Hello, everyone. We're live. So today we're discussing emergent gravity. So in particular, we're discussing Verlinde's emergent gravity model. And also, feel free to ask any questions that are physics related. So you can ask questions that are related to Verlinde's gravity that are on the topic of this video. You can also ask any kind of questions that are related to physics. Because in the process of working on gravity, I've had to sort of basically learn like every aspect of physics that I could. Um, um, and I'm trying to make these videos like accessible to a wider audience than just like the elite academics. I'm trying to make it more available to everyone. So basically, you can come in with your questions at whatever level of math or physics that you're at currently. Um, so go ahead and hit me up. Uh, let's see. Okay, so um, kind of what we've been building up to. Uh, so what I've been discussing is this equation here. So I've sort of been building it one video at a time. This is the first law of thermodynamics. Um, and so these T1, DS1, and T2, these are temperature and entropy terms. And then basically what I've been explaining is how these entropy terms can power this F grav term here. So this would be the force of gravity. So what I've been explaining in each of these videos is how these entropy terms could actually power the gravitational term. Um, so basically, the TDS, these are the heat energies, and then I've been explaining how modern physics can reasonably convert these heat energy terms into the work energy terms, and in particular, the force of gravity. And what I've been building up to is how the thermodynamics can actually derive Newtonian gravity. And the purpose of researching this is because quantum gravity is not renormalizable in the ultraviolet. And so, um, and so by incorporating thermodynamics and information science, we're actually able to bypass the part of quantum gravity that fails, and we're able to bypass that and come up with a self-contained theory that explains gravity. Um, in particular, we're talking about gravity at the high energy and uh, really like microscopic scale. So we're talking about like the Planck scale here, right? Like super small. Um, and basically that's where quantum gravity is stuck. And what I've been explaining is how emergent gravity, once we're finished building it, should be able to sort of overcome that shortcoming of quantum gravity and string theory. Um, uh, eventually, uh, eventually, I want to get deeper into string theory as well. Possibly, um, possibly identify some of the issues with string theory and work on those as well. So I'm thinking about combining the various gravity systems into like one system and kind of keeping like everything that works. Um, Hi Lilith, how are you doing today? Um, Okay, so that's kind of what we've been working on. So now in the Verlinde model, we can uh, we can start with sort of a simple example. So if you imagine like, so let's say you have like the planet Earth, um, and and then you have like one molecule of helium or something that's sort of being attracted to Earth by gravitation. So that would be a good example of the scales that we're dealing with when we're talking about emergent gravity. And one of the approximations that we can make is we can suppose that the Earth is uniform mass density. We can also pretend that the Earth is spherical. Well, I mean it is spherical, but what I mean is like a perfect sphere, right? So it's not like oblong, elongated or anything like that. Um, so we can assume that it's a perfect sphere, and uh, we can also assume that the mass is uniformly distributed. And both of these assumptions aren't right, but they're close enough that we can get at least Newton's gravity as an approximation by making these assumptions. So starting with those assumptions, um, and then so you imagine that the Earth is at the center. So here, so this is like a spherical surface, and the Earth is in the middle of this. Now this surface can extend into space. So the Earth is somewhere in the center of this sphere, right? And then the surface is in space somewhere, and the surface is also spherical. And then you imagine that your molecule is next to the surface, right? So let's say it's next to one of these red spots, and then we can talk about how this can actually derive gravity. Um, okay, so hopefully those approximations are kind of obvious that I'm making here. And then so so one of the things that I want to discuss in possibly the next video are black holes. Um, and so in the example of a black hole, the singularity would be in the center of this surface, which we're calling the holographic screen, right? And so the black hole singularity would be in the center, and then you would put this holographic screen on the event horizon of the black hole, right? And then the black hole would be acting on particles gravitationally and pulling them in. So the reason I bring up black holes now is because here, instead of a black hole, we have like a spherical planet in the center instead of a singularity. And then instead of an event horizon, we have a holographic surface in space, right? Instead of an event horizon. So the event horizon would be an example of one of the situations where this model could be extremely useful, um, especially to certain areas of physics that are not currently known. So near the event horizon of a black hole is where physics does not know exactly what happens to the matter. Um, that's something that I can discuss possibly in the next video, possibly. But today we're talking about the Verlinde's gravitational model. Um, now one of the things that I've mentioned before. Let me see. So this is the en route temperature here. Oh, it came out kind of pixelated. So this is the en route temperature. And one of the things that I've been mentioning is that the Unruh radiation is almost identical to the Hawking radiation. Now, the Hawking radiation is evaporating from the black holes. Um, so you can almost think of the Unruh radiation as like evaporating from the vacuum of space. And it's also evaporating, or you could think of it like it's evaporating um, from these screens. So these holographic screens here. You can think of it as though this radiation is evaporating from the screens, right? So it's sort of like um, I mean, it's the temperature of the screen first of all. It's like how hot the screen is. Um, um, but what I've been explaining is how that heat is actually driving gravitation itself. And then I've been talking about, these are the partitions are like sort of like pixels on the screen, um, and each pixel is like a Planck area, and each pixel holds one bit, um, which is a quantum bit called a qubit, and each pixel holds one bit of entropy. And then remember the entropy times the temperature. So this T is the temperature, and the entropy times the temperature gives you the heat, right? The heat, and then this heat is getting changed into work using this first law equation. So the heat's getting changed into work, and then you have an emergent force, F grav. That's an emergent force. And as the heat is changed into work, then it generates the Newtonian gravitational field. Um, so that's pretty much what we've been working on in all of these videos. What I've been working on explaining. Um, uh, okay. So you have the holographic screen. Um, and you have a particle that's near the screen being acted on by gravitation. And then next, basically we have an entropy step. Oh wait, did I finish the Unruh equation? Let me not get ahead of myself here. Okay, so we already discussed the Unruh temperature, but doing it in even more detail. Um, uh, so um, so A is the acceleration that the particle being acted on by gravitation would experience, right? Um, so if there is a gravitational field, then the field is applying forces on the particle, and then the particle experiences an acceleration from the field. But what we've been discussing is that if there's an acceleration, then the quantum field theory insists that there must also be a temperature that corresponds to the acceleration a. So if the particle experiences acceleration, then the space um, in which the field is being generated must also have be experiencing a temperature T. And h bar is, of course, Planck's reduced constant, which shows up in most of these equations. It's basically like a scale. Basically, the quantum scale that we're dealing with here is when you see an h bar, you know that there's something quantum going on. And of course, c is the speed of light in a vacuum. So the speed of light has something to do with the radiation of the space. Um, and so you can see that there's, or you can see the sense in which I consider force to be holographic, because there's this correspondence between the temperature of the field um, and the frame of reality that's experiencing the force. There's a correspondence. The temperature is in the ambient space, um, and so you can think of another aspect of the holographic principle being that there's a direct um, dual or dual. Am I using the right word? There's a direct correspondence um, between the temperature of the field around the particle and the force that's experienced by the particle. There's a direct correspondence here in the Unruh temperature, and these holographic surfaces are radiating. Um, and so it's not much of a logical leap to say that there's a direct correspondence between the force field and the temperature of the field. Um, so what if thermodynamics is essentially powering Newtonian forces such as gravity? It's not much of a leap. Once you establish these facts, it's not much of a logical leap to make that like realization that that the force field could be generated by thermodynamics. So, in other words, gravity is acting similar to, like an engine, for example, or um, I mean, I don't want to say it's like a rubber band, but um, like it's kind of like similar to a rubber band in certain ways, certain specific ways. It's similar to gravity is similar to a rubber band because the rubber band, the little monomers in the rubber band, they have like entropy, right, and they have temperature. Um, uh, so like when you're stretching the rubber band, it resists, like the elasticity like resists when you're stretching it, right? But I don't want you to think that gravity is literally a rubber band. That's just like an analogy uh, to start to kind of understand what it really is, right? Let me see. Okay, no comments yet. And like I said, feel free. You can ask anything that's physics related. Um, it doesn't have to be about gravity. It could be anything physics. Um, anything physics. Okay, so that's sort of my first pass of the Verlinde gravitational model. That's sort of my first pass, and I'm going to be developing it in more detail as we go. So basically, we have like the engine analogy. We have the polymer analogy of things that that is similar to how I believe that gravity is being manifested as an emergent force or an entropic force. And what I think I'm going to cover in the next video is more than an analogy. The it's a specific example of a case where this model would be useful, which is to analyze a black hole. Um, so so a black hole would be a literal example of what of how gravity works um, at these uh, at these Planck scales, the Planck length scales, um, and um, we also have like the black hole information paradox, which I'm pretty sure I know the answer to it, and I can explain what I mean. Um, but yeah, I'm pretty sure I know the answer to the black hole information paradox. Um, and um, and then I want to change the question from what happens within a Planck length of the black hole's event horizon. I want to change that to what happens within one Compton wavelength of the particle next to the black hole, or next to the event horizon of the black hole, right? So that's something that I can cover next. Um, Mike, bending light around stars as at a rate. Oh, yeah. So that was yeah. Okay. That was one of the earlier like verifications of general relativity. Um, and I suppose it would be better to say relativity. I want to make sure I get my classification right. Yeah, I'm going to say relativity. Um, so basically, when you have a gravity well, um, and the sun was eclipsed, what you saw uh, was basically that gravity well is acting almost like a magnifying glass. Um, so like if you've ever like used a magnifying glass, you can turn it both ways, and like one side makes everything smaller, and then the other side makes everything bigger, right? So basically, the theory of relativity like is saying sort of, um, oh, okay. So yeah, so the theory of relativity is basically saying that the gravitational field is like a magnifying glass, right? Or not only the gravitational field, but space-time. Space-time itself, like space plus time, is like warped, and then you have the lensing effect, and so they made this prediction, um, and then and then that was a testable prediction. So they waited until there was an eclipse in front of the sun, so that because obviously you wouldn't see the stars near the sun if it's daytime, right? So basically they waited until there was an eclipse, and then they could see the stars, and then they found that there was the positions of the stars moved in correspondence with the lensing effect. And so then they verified that prediction. So it made a testable prediction uh, for relativity, and then they verified it. So that's gravitational lensing. Um, so let's see, elasticity. Um, let's see, how does that relate to elasticity? Okay, I think I get what you're saying. Yeah. Yeah. So you can think of like the space is getting like elastic in some sense. I think that's a good analogy, actually. Um, yeah, that makes sense to me. Yeah, I like that. It's almost like the space time is like stretching, right? I think that's what you're saying. Um, and yeah, that makes sense. And then the stretching of the space time. leads to gravitational lensing, which was one of the early um, predictions of relativity that was successfully tested, and came back as a confirmation that something about relativity is legit. Um, so I hope that makes sense. Um, okay. So if there's no other questions or comments, feel free to post your questions, comments, after I close down the video. Uh, or if you're on YouTube, feel free to leave a YouTube comment. Or you can always shoot me a message in Messenger. Um, um, okay, so if there's no other comments, have a great rest of your day.